real job after PhD because he was at IBM TJ Watson Research Center, and I was a student intern the year before, and I went back to give a talk, and then there were like maybe my talk was very well received. Maybe 5 people were in the audience, and Lav was there, and then he pointed me to, hey, our group actually is hiring, so that's where I get to know the hiring manager and then joined the team, which then I immediately was blown away by just how productive Lav was. I think you were filing like 5 patents per week, something, if I'm counting.
Not quite.
But he's a mastermind between Chef Watson. Many of you may have heard about this. And that's before generative AI and was a thing. And Lav pioneered this line of work called computational creativity. The idea was to thinking about creativity as a combinatorial process and this very high-dimensional space, and how do you use computationally to generate great new ideas. And his test bed was on recipes and how do we think about using the principled flavor networks to think about generate recipes that we have never seen but will taste very well. That was his brainchild. Smashing success in a way that I've never seen anything that is this successful at IBM Research. And then he left and joined UIUC, and then he continued to do a series of very, very interesting work, and including more recently, he just finished his service to the government and came back from White House, where he spent a year in the government to help us think about the AI, National AI Act. So, and this year, he's spending his sabbatical year at the Ryan Institute. So we're very excited to have him and to give this talk. Yeah, thank you.
Thank you, Darshan. So yeah, I thought I'd talk about engineering theory a little bit and how it might be relevant for strategy and policy. Even engineers often don't think engineering theory is useful, so I'm hoping to make the case that that it is actually relevant in certain ways. And I'm also going to talk a little bit about the startup I'm involved in called Co-Create, which is taking that idea of combinational and computational creativity forward as well. So, you know, as Joshua mentioned, I've been thinking about policy now for the last 2-3 years, and I think a lot of the same ideas that are coming up in national policy in terms of national competitiveness and national security are also actually super relevant in terms of business strategy. So I'm going to try to allude to that a little bit as well. Okay, so as Darshan was mentioning, we've been thinking about AI for design and operation and maintenance of engineering systems for quite a while. So this is an example out of the Chef Watson system, and in fact, that technology has been pretty successful. A lot of the things you can buy in grocery stores are actually developed using the technology. So McCormick spice mixes and all kinds of things that are still under NDA. But you can use AI for a lot of things. So this is a nice example where we developed concrete formulations using AI. The nice thing with these is that they require half the carbon, half the embodied carbon as traditional concrete, but they're actually more strong and they appear more quickly. And this was deployed at our data center in DeKalb, not far from here. So Meta was building this $1.2 billion data center, and so they poured our concrete. And they're actually using it now in their data centers in Minnesota, and all the hyperscalers are going to be using our concrete ideas. Concrete, the building material, not concrete, the adjective. So, so we're pretty excited. So, because if you can reduce the carbon requirements for concrete, that's about 8% of global emissions. So, if you have that, like we were able to do, that's the equivalent of removing all aviation from the world. So, aviation is only 3% of global emissions. Concrete is 8%. So, we're pretty excited about this and various other problems in areas like protein design as well as wastewater treatment. Another kind of broad area where AI seems to be getting to be pretty powerful is in music. And so we've been working with a lot of music programs, whether it's Hip Hop Express in Champaign or Musical Arts Institute in Chicago and elsewhere. And what we've been thinking about is how do you take music, decompose it into abstract pieces of rhythm, harmony, melody, and so on, and then recombine at that higher level of composition. And this both lowers the bar to creativity, but also allows everyone to monetize creativity. Traditionally, people have felt that their creativity was stolen by record labels. These days, it's AI that's different than what we do that seems to be scraping and stealing. And so I'll get to this a little bit at the end of the talk, but we've developed a technique called information lattice learning, which is very IP friendly. The foundation lattice is trained literally on 370 chorales by Johann Sebastian Bach. And then all the individual pieces are fully traceable and attributable rather than mashed together into neural lanes. And so you can actually give credit back to everyone who uses your pieces of music to do further composition. So
you're getting basically a new Bach-like piece where each part has an arrow back to some other Bach piece.
Yeah, no, but it doesn't have to be Bach. So so the foundation is Bach, and that's like a tool. Yeah, so it's a tool, but then yeah, like if it's me or if it's Taylor Swift or Dr. Dre or if it's the great Ben Jones, right? I mean, you can attribute it back to anyone. Yep, that's exactly right.
Wow.
So so we're excited about that as well. And what I wanted to kind of focus on is this broader idea that with growing developments in emerging technologies, whether it's AI or quantum or other things, there's becoming a very, very strong nexus between public policy on the one hand and business strategy on the other. And we did this report with Rand Corporation. It came out about a month ago. And what we were arguing in this report is that we want to be kind of not putting all our eggs into the hyperscaling of large language models basket. That there are multiple paths to perhaps to AGI. And if as a country or as a company, if you just focus on that one approach, then you're not hedging against other possibilities. And I think that's generally true. That there's this public policy element with respect to national competitiveness, and I think it's the same for individual businesses as well. And so that's where we're kind of coming from with this company that I've started called Concrete. Here we're using a technology called information lattice learning, which goes back in some sense to Claude Shannon's lattice theory of information, which is quite obscure. He presented it at the 1950 London Symposium on Information Theory, and then there hadn't really been any work following up in the last 75 years until my former student Heisey and we really kind of pushed it forward. If you're a scientometrician, like many of you in the audience, there's 200 citations to that lattice theory of information by Shannon, but only 20 of them are actually meant to be citing that paper. 180 of them are kind of miscitations to his 1948 paper. Right, so I mean, quite obscure. Right, so okay, so what we wanted to do is kind of think about kind of charting these multiple courses to AGI. So information lattices is one approach. And broadly speaking, it's nice because it emerges out of engineering theory. It comes out of information theory, which is distinct from, say, neural networks, which are coming kind of more from kind of biological inspiration in some sense. Okay. And the other thing I wanted to kind of touch on as kind of a second motivation for this kind of thinking around policymaking and strategy is that we want to take a socio-technical perspective, especially with respect to emerging technology. And so what that means is to view society and technology together as one coherent system. And the claim is that it's not possible to understand the social without the technical, nor the technical without the social. And what I mean by this is that public policy or business strategy is more than just applied political economy. It's not simply about addressing market failures like information asymmetries or externalities or collective action problems, which is very much that political economy view of what policymaking should be. But there's more to it than that. And in particular, I think the technical is actually understanding that at a deep level is very important for these emerging tech questions. Typically, when people talk about the socio-technical, they mean this, right? Make sure you keep the social in the socio-technical, right? What I'm saying is maybe we've swung a little bit too far and we've lost the technical in socio-technical. So that's kind of one of the arguments
So the plug of the second paragraph here about market failures and different functionalities, et cetera.
Yeah.
So I don't see why, to me at least, technology wouldn't also appear there with lots of externalities. So is there some other force that we should think of that's not an externality or a collective action problem, or is it that we need to take those ideas and also use them to think about technology?
Yeah, so I think the way I've seen it, and you can correct me, but the way I think political economists typically view it is that they abstract the technology itself and they view it simply as a information asymmetry problem or something like that, whereas they do not take the details of the technology into account specifically. And I think that's a bit of a gap that leads sometimes to paths that are not the best in terms of policymaking.
Can you give me like an example of it? So is technology detail the other one?
Yeah, so as an example, many people think of technology as a complement to labor or to capital, but they don't think about how it might actually change the innovation process itself. So that would be an example of where an abstraction of technology is simply a complement to labor, is not digging into the technology itself. Yeah.
I'm also going back just a little bit to something.
Mm-hmm.
We were talking about this relationship between public policy and business strategy.
Right.
So in business strategy, it's often defined the outcome that you want. I want to maximize profitability. I want to maximize. Is that also true in public policy?
Yeah. So again, I'm just from the practice of it. It seems to me that like a country like the United States, it has many different objectives. There's questions around economic strength, there's national security, mm-hmm. There's questions of equity. I mean, there's a lot of potential objectives. And what I was trying to argue is that for sure, as a country like the United States, we have a lot of things that we care about, and businesses broadly have like a single focus, making more money or creating shareholder value or so. But I think they've become quite interlinked. So these large companies that are dominating the news, they seem to have a disproportionate impact on many of these factors. And so as these companies are thinking about their strategy, it's very linked to the public policy questions that are arising as well. And that's why I think it's a useful idea to think of them in some joint manner. So that's kind of my way of thinking about it.
Yeah, if I could just follow up, I mean, it seemed to me like some of those things are really incompatible with each other. Maximizing profitability or returns to shareholders, things that really don't exist in the public realm, and that could in many ways undercover the public policy is meant to do. Are you going to talk about that?
I'll hint at it, but I think it's a deeper question that I'm still thinking about. So I agree with you. And yeah, as I was mentioning, this is kind of a new talk, so lots of holes to be filled. So hoping that this audience will help me do that. Okay. When people talk about socio-technical policymaking, they often point to this idea of avoiding abstraction traps. This paper by Phelps et al. They talk about framing, portability, formalism, ripple effect, and solutionism. And these are, again, just largely focused on abstracting the social and only focusing on the technical. On the other hand, like I was mentioning, I think it's become kind of a flip. So in fact, the technological details have become too abstracted. And so it's kind of a new kind of abstraction trap of not caring about the technology itself. Okay. And to quote from this textbook by Dorfman, Samuelson, and Sola, so to give another example, Ben, so for example, the Cobb-Douglas production function or similar things. So technologists regard those production functions as an economist concept, and as a matter of history, nearly all the production functions that have actually been derived are the works of economists rather than of engineers. Right? And so, yeah, like I was saying, the impact of technology is not just in rebalancing labor and capital, and this seems to happen not just in Samuelson and Solo's day, but still today. All of these kind of ways of thinking about the impact of technology on economic or social productivity abstract, it seems to me, a little bit too much. Cool. The other thing I think that's often abstracted is when people think about engineering systems, they either think about these kinds of things, these big and specific physical infrastructure. So if you go down the road from here, there's the Thornton Composite Reservoir. It's the size of 14 soldier fields, I think. I mean, it's a huge, huge thing. It has 7.9 billion gallons of water and so on. And as you might know from history, reversing the Chicago River was perhaps the biggest engineering project in history. Okay? So when some people think about, especially policymakers that I interact with, they think about engineering systems as either something like this, these like big things, or they think about very small and specific things like chips. Right? And there's actually a whole spectrum of kind of engineering questions and technologies in between kind of the big old things and these very microscopic things. And again, I think that as far as I can tell, that creates a little bit of a blind spot when one's thinking about technology policy. There's things that you can do in between. And then a third kind of thing that has kind of troubled me sometimes is when people think about engineering systems or engineering processes, they often think that it is largely just hacking, kind of hacking things together without having a strong theoretical foundation. So if you ever saw this movie from Bollywood called Three Idiots, so this central character is very creative. He designs all kinds of things. He hacks together junk and makes pretty cool stuff. Likewise, this book that's popular among among children my kids' age, Rose de Revere Engineer. It's all about taking junk and building stuff out of it. Right? It's a very, very narrow view of kind of how engineering seems to work. But again, that is often how at least many policymakers that I interact with seem to approach it. That there's no obvious way the belief is to predict or design or abstract things in such a way that you can get results in the manner that you predict. Okay, good. So, so this is kind of some of the motivational aspects of why I've been thinking a lot about the use of engineering theory for policymaking. I kind of pose some straw men, but now let me dig into like kind of some examples. Right, so this is the kind of engineering theory that many would regard as kind of very natural. What you would do is do some network science analysis. You look at food flows across the United States, and you try to find where are the choke points, and this would be helpful for infrastructure policy. So you would say the port of Long Beach in California is a key choke point. So if I wanted to invest more in protecting infrastructure, that's where I would do it. Okay, and this is really a great thing to do. I mean, we wrote this paper that was on the cover of Nature, Food, and so on. But this isn't the kind of engineering theory I'm talking about. This is kind of looking at specific systems and asking their properties. Another example of kind of this specific kind of thing is suppose we have a city like Syracuse in New York, which is also my hometown. So what one could do is try to predict which houses are easy to flip back to occupancy that have become vacant. And that has huge impacts on urban blight and kind of community strength. And so we did this quite a while ago. And this is actually, again, very effective. I think the mayor attributed just in the first year of this program to be able to do these land bank policies. I think it was like $5 million of impact right in the first year. Right, so again, kind of using a machine learning algorithm for the operations of the government. Again, very specific. Again, powerful, but not the kind of engineering theory. And one could also do stuff like agricultural policy. So one can predict the impacts of climate change using AI techniques. And this is actually our family's farm down in Urbana. So we grow corn and soybean. And so, my wife is mostly running this, but, we talk about what's going to happen in 100 years. Is the farm still going to be able to grow corn? And so, predicting the future of things is very important. But again, it's very specific, not the kind of engineering theory I mean. Okay. Right, so what is the kind of engineering theory I mean? Okay, so this is the kind that I mean. So drawing on this book by Sunny Oyan. So what she says is that engineering systems theories respect the constraints of physical laws, but being theories of what can be of use, they abstract from the most physical details to allow the maximum freedom for ingenuity to create useful artifacts. And so they're very much this abstraction. They're not concerned with specific phenomenology, but are meant to be kind of general characterizations. Okay, so kind of three examples are the following. So Carnot established the fundamental limits on the efficiency of engines, kind of the founding result of thermodynamics. And so what he said was that no engine can be more efficient than this particular Carnot limit. Likewise, Shannon argued that there's a fundamental limit to the transmission of reliable information in the presence of noise. If you try to send more bits than the channel capacity, then you'll get error probabilities going to 1. Right, so you cannot communicate more bits than the channel supports. And likewise, Karaman and Frisoli, they established this fundamental speed limit of flight in forests without crashing. So if you try to fly faster than the speed limit, you'll crash infinitely often into trees. And if you're below that speed limit, then you can go forever without crashing. You can maneuver quickly enough. Sertaj Karaman was actually my roommate in grad school, and I like to take credit for some of this because I was fairly messy in our living room, so you have to navigate around a little bit. Right, so these are the styles of things that I'm trying to talk about, is these fundamental limits. So if you are below this, you can do things really well. If you're above this, it's impossible.
So I mean, the question, just like the title of the book is mimicking science, the endless frontier, right?
Right.
So then the question in my mind is always, engineering is also different than science. And so I think, you know, if you look at the limits like Carnot, for example, it seems to me that's the sort of the scientific discovery. It doesn't have to be Carnot. Somebody else will discover this is the limit you cannot traverse.
Right.
So that sounds to me, that's always been a key characteristics of science, is that, you know, we're really discovering it, and it's always been there. Whereas, how do you build an engine to get closer to that limit?
Right.
That's, you know, engineer dependent. You know, who builds that depends on that, right?
Yep.
So that's where I wonder if you distinguish these two cases. And same, I think for Shannon, it doesn't have to be Shannon. One day people will discover there's fundamental limits implied by entropy, but then how do you build a communication channel to get close to that? That sounds to me is squarely for engineering systems, right?
Yep. So let me get to that. I agree with you. And so where did these limit theorems come from, and then how do you get to them? So Bruno Latour, the anthropologist of science, what he described is that Carnot's know-how is not about building a machine, but rather a diagram. This diagram is drawn in such a way that it allows one to move from one engine to any other, and indeed to non-existent engines drawn on paper. Right? The whole point is that abstraction is very key. Likewise, Shannon himself argued that you know, he cast various things out of information theory. He said that messages might have meaning; they are correlated to certain physical things, but these semantic aspects of communication are irrelevant to the engineering problem. So anything in the diagram is communication; everything not captured by the diagram is not. Right? So he's abstracting what communication is. Yep.
So you do a lot of patenting.
I've done some. Yeah.
Yeah. So, you know, patents are fundamentally made up of diagrams and text. Right. Is that contradictory to what Shannon is saying here, though? I mean, you can't really interpret a patent unless you put both of those things together. They're both relevant to the interpretation of each other.
Yeah. I mean, this diagram is from his paper, as is the text. Yeah. So, I mean, the explanation and the depiction are I mean, they go together. And actually, in this particular example that I'm very familiar with, like, there's almost a formula of how the language works. So there's always this phrase, arbitrarily small error probability, right? As the system size increases, like that formula goes with the picture. Like, you can't have one without the other. If you're familiar with this philologist from Stanford, Reviel Netz, he did this work on Greek mathematics. And again, so it's, you know, Euclid and all these guys, they drew diagrams and then they had text about their geometric proofs. Again, they were very formulaic, like in how the words went with the pictures. And it seems to me that that's actually generally true in all of these settings, that somehow there needs to be a linkage between the two.
All right, so then I don't understand why it says semantic aspects of communication are relevant to the engineering part.
Yeah, so he was, and I can give you my own kind of example of this. So I've been working on this mathematical theory of creativity for some time. And whenever I presented it initially to, like, say, humanist audiences, they would always ask me, what about the intentionality of the artist? Isn't that very core to creativity? That wasn't captured in the initial version of my theory. And I finally understood why Shannon had this sentence, because I'm sure everyone he talked to about his mathematical theory communication would ask him, what about the semantics, right? And so I think broadly what he was doing is saying that this is the technical problem of communication, getting signals from one point to the other with a small error probability. And then you have to build the other things on top of it. And so the core of the theory is really this kind of engineering problem as he described it. And then there's other layers beyond that. Right, and so the core of information theory is only about kind of valid reconstruction of signals, whereas the semantics are then added on top of it.
Okay.
Yep. Cool. So can you define limits for other things? So it turns out you can for things like decision making. So you can try to estimate how well you can do classification. So a lot of people have spent a lot of time building classifiers for these various standard benchmark data sets. And this is actually an estimate of the fundamental limit, and this is what the state of the art is. And so you can see there, these are just below the state of the art. And so, so this is an example where you can see that what people have been able to do, what engineers like Darshan was describing are actually able to achieve, is actually pretty close to the fundamental limits, right? So this is kind of a nice example of that. You can do the same kind of thing for creativity, like I was describing, for nanoscale computing, for deepfake detection, et cetera, et cetera. So you can try to define these fundamental limits for all kinds of informational and related systems. Okay. And now coming back to Darshan's question in a sense. So Pierce tried to argue in this book from 1965 on fault-tolerant computing that what every engineer needs is a good set of limit theorems. Okay. And one might wonder why, right? So why does one need limit theorems? Why can't just one build stuff and see what happens, right? Take the Rosie Revere engineer view, like just try building stuff and see what happens. And I think that is one approach, but I think that limits what one can do for strategy and policy. So what fundamental limit theorems allow you to do is establish, so the fundamental part of fundamental limit theorems allow you to establish which resources and performance criteria are fundamental and which are largely unimportant. Right, so this is part of what Shannon was trying to say is, like I care about number of bits that are getting across reliably. I don't care at the moment, at least, about what those bits mean. It demarcates what's possible from what is impossible. So it provides design insights into operating at that boundary, which is to say kind of architectures for optimal designs. And then third, defines fundamental benchmarks, like we saw with the machine learning example just now. So this is the best I can do. So I want to compare my algorithms not to the previous algorithm, but actually what's the best possible thing I could do. And fourth, it actually pushes people to build technologies to approach those limits. So these are four kind of the traditional view of why limit theorems are helpful. I want to add a fifth one. It kind of characterizes probabilities and possibilities of what-if scenarios. So when there's deep uncertainty about technology going into the future, when you're doing policy making, when you're strategizing about the future, these limit theorems will tell you kind of what's possible and impossible. And so you can actually kind of reason in these settings of deep uncertainty. Which is difficult if you're only looking at point solutions of actual technology. Cool. And so yeah, one of the reasons I've been thinking about this is actually goes back to a faculty interview I did about 15 years ago. So I was in, let me not name the school, but so I was interviewing somewhere, and it was an electrical engineering department, and this audience member asked me like, "Oh, you're an information theorist. Why should I care about information theory?" Like, why can't I just build stuff, right? Which is maybe an unfair question for a job talk, but I mean, that's a separate question. But, you know, it's kind of it's stuck in my head now for a long time, right? So like, is theory actually useful? And what I've tried to argue here is, yeah, I mean, it is in some sense, but what about outside of engineering? Is it useful? And so one kind of field where it seems to be, and again, being a little parochial and using my own examples. So in theoretical neuroscience, it seems to be useful. So information theory ideas allow you to understand the limits on how much people can remember. They'll allow you to reason about limits on how people perceive or how quickly organisms can act and so on. Right. So there seems to be some usefulness for it. But what about for policy and strategy? So our friend Vannevar Bush, right? So he was very much a proponent of this endless frontier. So hopefully everyone recognizes this guy right here, right? But does anyone know who this guy is, who just barely made the publicity photo? Yeah, this is actually Claude Shannon. So he worked for Bush. And so yeah, he was working on the differential analyzer, and he just made the cut. And so you know, Bush had this kind of philosophy of the endless frontier, whereas Shannon was the big proponent of fundamental limits, right? And so how should we view things? Should we view it as if we can be kind of as unbounded as we can, or should we be thinking in a more constrained manner? Yeah, but
I mean, to me, the endless frontier is the support. It's the X variable. So in a limit, you're limiting the size of the height of the mountain, right? But you're not limiting how far you can go towards. I mean, you can go to infinity on the X-axis. And I sort of feel like those are. I kind of think like Vannevar Bush is talking about the X-axis, and all these limit theorems are about the Y-axis.
Right, but so suppose we can keep going on the X-axis, but it doesn't buy you anything on the Y-axis.
No, it's good to know that. I mean, that goes back to your prior point that it's awfully useful to know that the maximum gain I could get would be another 1% or something, because you might as well redirect your effort somewhere else.
Right.
Exactly. But still, the idea that this is not like, I think in some models in economics, your ability to keep improving, even if it's small, might be relieving some key bottleneck in the economy. So it doesn't actually mean that
It's not.
Yeah, you can grow infinitely even if you approach technology limit potentially. So it's not quite blatant. That's a side point, but I do think that these are not necessarily opposing ideas.
Yeah. I'm not saying that they're opposed, but I think one is more of a kind of philosophical point, and one is more of a practical point. And I think kind of keeping both in mind is perhaps a useful thing. Yep. Okay, so how can we use these kinds of engineering theories, not the network science to find the choke point in the Port of Long Beach, but information theory or those kinds of things for policy? So that's what I want to get to. Right, and this is almost getting there. So this is some work we did on tree planting with the Indian Forest Service. So some people have this view you can just keep planting trees wherever you want, and that'll be good for the environment, right? But it's not the case. And actually, like, strangely enough, this goes back to the British era. So there's these targets of like kind of bringing India's geographical area, like 2/3 of it under tree cover, right? And you actually try to do this, like it doesn't work. You just can't support that many trees in these environments, right? And so this fascination actually, I mean, like I said, has this kind of colonial history. But what we did was we drew on these ecological and biological principles. So there's something called the carrying capacity in mathematical ecology. And so you can actually compute the carrying capacity of Himachal Pradesh in India. And it's really only about 1/3 of the surface can be covered with trees and actually, thrive. And so, it's only half as what people are targeting. So you don't have this endless frontier, as it were, of just planting more trees. There's a fundamental limit to how many trees you could plant. Okay. So, and then we actually built some algorithms to suggest where to plant trees. And they're actually using that in the Indian Forest Service. So my collaborator, Pushpender Rana, is the conservator of forests in Himachal Pradesh, and so he's actually doing this kind of stuff. Right, so we have kind of this our understanding of limits, like what is the best you could do. You have the algorithms that are suggesting where to actually plant trees, and the question is, can you push this one to the limit, right? And kind of this helps with policy making, right? You don't even try for the 66%. I mean, he's convinced his higher ups that, I mean, this is just impossible. Like just let me try to aim for 30%. Like, don't try to push me to 60%. Okay, so let me briefly talk about kind of other avenues in which engineering theory might be useful for policymaking and strategy.
Right, so let's take energy for a second. So you have the Cornell limit. So I mean, but the goal, if the goal was energy efficiency, then you have a limit and you have to pay attention to it. But if your goal is like cheaper energy, say, or like abundant energy or clean energy,
right?
It's not entirely. I mean, that's an important limit, but of course you can find other ways to make energy. You can just make more of it. You can do fusion, or you could then you go cheaper and smaller or something. So I mean, I would imagine, I don't know anything about forestry, but I also imagine that whatever that limit is coming from, there are probably ways to make trees that use less resources on the input side or something. And I'm not quite sure what the nature of the limit is, but
non-natives.
Sorry,
non-natives. Non-native species. Like
exactly. You could technologically advance the seeds or something, or the microbes or the whatever's in the soil. I don't know what the nature of the limit is, but whatever it is.
Yeah.
I mean, sometimes in engineering we think of like engineering design limitations, but actually the system itself is much more flexible.
Yeah, that's true.
Right.
Yeah.
And so how do we think about, like, I mean, we don't want to over-attend to a limit to as some kind of a possibility theorem, because actually usually for the objective, it's not the limit per se, it's just kind of a limit in the system that has more complex components and the objective is elsewhere.
Yeah. I mean, that's exactly right. So, so that goes back to the fundamental part. So you have to define the playing field, like what is actually under design. And once you kind of fix that, just like Shannon said, like I have this diagram, I can change things that are within that diagram, but I'm assuming I cannot change them beyond that. But like even with communications, you can actually change the physical channel. Like, I can move closer to you, I reduce the noise, right? And so the capacity increases. If I move further back, there's more noise and, the capacity decreases. So of course, there's all these other things that are either parameterize the fundamental limits or are part of these broader systems that allow this kind of thing. So completely agree. But I still think these limits are helpful as part of that thinking. So I know exactly, like, so if I move this much closer, how much does that increase the capacity? Things like that.
Well, I mean, sometimes sorry.
Oh, no.
Sometimes the limits are directive because you would say when the guys at GE say, you know what, we're going to put $1 billion into increasing energy efficiency on this turbine.
Right.
And someone might raise their hand and say, you can't do that. We should make, cheaper turbine blades or something, like you're like, yes. And I mean, so I think it's very directive, maybe because it moves you away from the limit.
Right.
But still, but that was sort of, so I get your point, but I think it's that limit.
Yeah, good.
So I have a similar question. I've been thinking about a single limit, but what do you do in systems where there's multiple limits? Which limit do you choose? How do you aggregate them? How do you make a decision about what you're going to pay attention to? So maybe there's a limit on the size of a plane I could build. But then you got to worry about the limit of the size of runways that they can land on. They got to you got the limit of temperature, you got the limit of the number of passengers, all this sort of stuff. How do you make those kind of difficult?
Yeah, actually, James Evans and I have a DARPA grant that's looking at creativity under many functional constraints simultaneously. So we're thinking about it. Yeah. So what we're trying to do is actually extend my mathematical theory of creativity to have consider settings where you have many of these possible constraints. So yeah, I hope to have some things to tell you in a few months.
But is that get worked into the engineering theory part? Or is that bringing in another set of ideas to make that work?
No, we're pretty sure we can extend that basic theory to have these multiple functionality requirements, etc. So I mean, we're almost there. So hope to have stuff to report in a few months.
Okay.
Yeah. Okay. So so as I said, so this kind of engineering theory, I think, is useful for informing policymaking itself. But also it can be a policy lever, which is kind of maybe an unusual use of theory. So I'll come back to this in a bit. So I want to discuss kind of 3 examples of where such engineering theory might inform policymaking. So some years ago, I was at Salesforce, and we built this large language model that had 1 billion parameters. It was state of the art at the time, better than GPT-2, et cetera. And then, ChatGPT came out, was seemingly better. I mean, maybe not so much better, but their form factor was good. This is still actually pretty fluent and so on from 2019. So I was in Washington when this came out in November of 2022. And, as we've been progressing, we've been seeing this kind of growth, some sort of scaling law, et cetera. And so, people that I served with decided that, there's some line right here and some other line right here, above which we should probably require reporting of what industry is doing. Okay? And so one might wonder, where does this line come from? And why should we have such a line? Okay? So if you're a regulator, you have the possibility of regulating like money or compute or data or something. But what you really care about are capabilities, right? I mean, the premise of regulatory policy in this area is that you want to be, aware of certain capabilities. Okay? This made it into the executive order that was, I helped write, but it was rescinded a few months ago, et cetera. Commerce did some further work, et cetera. There's actually some ongoing bills at the state level that are, taking up some of this same kind of question. So what we want to ask is, so is there an engineering theory that relates resources to capabilities that would provide kind of solid footing for such regulatory policy? So if you could translate things like data or compute into capabilities, that would be really helpful. And so what we tried to do in my group is develop a theory of scaling and emergent capabilities and plateaus as well. Let me skip some of the details, but what we found was that, first of all, you do have to increase compute linearly with data set size, or you can do it the other way. The so-called chinchilla scaling is actually helpful. This was previously just an empirical observation, but we were able to prove that this is actually exactly what we do. Moreover, that there actually are phase transitions. There is this emergent property. So as you increase the size of these large neural networks, there is a point at which they significantly increase the but also there's actually this plateau and then multiple emergencies. So it's possible you could have plateaus followed by another phase transition plateau and another phase transition. And so this has not been seen empirically yet, really, but it's something that we kind of predict out of we explain known things and predict some things. And further, with the so-called inference compute scaling, you actually want sub-chinchilla as well. And so this is kind of where we were trying to say, there's some relationship between capabilities and resources. And this is one area where engineering theory is helpful. A second area where engineering theory might be helpful is what's called net assessment in national security settings. You want to understand how you compare against your adversary. And when you do this for, say, like semiconductors, so like when you're building chips, semiconductor energy, there's no known lower bound to this. You can, in principle, keep going. It's not just zero. I mean, there's a zero at the bottom of this, but nothing tighter than zero. Right? So how do you know when to stop? Or if you're looking at communications, we do have a fundamental. So if you're within 0.0045 dB of the Shannon limit, you're pretty good. You can maybe stop at some. And so if you have these absolute scales, it's actually super helpful from a strategy perspective, also from a national competitiveness net assessment perspective. So if you and China are both within 0.0045 dB, I mean, does it really matter? You can kind of stop, right? So this idea of having these fundamental limits allows absolute scales rather than relative ones, and these scales can come from engineering theory. The other thing that you can try to think through out of engineering theory is, yeah, go ahead.
I mean, I guess my question is, but how often? I mean, we have some limits that we know that are really important, like Carnot and Gen information limits.
Yeah.
But like otherwise, I mean, how often are there really limits?
Yeah, I mean, one needs to develop them for various areas. So yeah, I mean, that's been a lot of my own effort over the last many years. But there's a whole community that's working on these things. So yeah, I mean, I think they're absent in certain areas, they're present in others, and when we have them, we should use them.
Absolutely, but I guess I'm saying like, this is maybe an impossible question to measure or scale,
Yeah.
but like, are we talking like 4% of engineering problems and directives have functioning limits, or is it like 40%?
Yeah, I don't know how to answer that
Yeah, okay.
question. Yeah. It's a good one though. Yeah, like just to take this example I'd shown before, like this one is very like, I mean, again, I'm an author on this, so I'm being a little parochial about it, but you know, like understanding the limits of discrimination and all these standard benchmark tasks, like I think is actually quite useful for this kind of thing. And you can do this for a lot of AI tasks. Okay, good. The other thing that one can do out of engineering theory is actually get architectures. So like what is, like how do you build things that are optimal? And someone I started with, Kirk Campbell, he was the Deputy Secretary of State eventually. So he was trying to argue that, you know, we want to have resilience in our supply chains rather than just efficiency and so on. So suppose I take the semiconductor example. So how can we architect multiple paths to be more resilient? I'll skip a little bit of the details, but roughly speaking, working with some computer architects at Illinois, what we tried to argue is that there's 3 techniques you can use. So composition, allowing bigger chips to be constructed out of smaller ones. The adaptation, the ability to actually change how chips are used, and then dispersion such that you can have many suppliers for things in the supply chain. And broadly speaking, kind of chip architecture has not been connected to the supply chain itself. They're typically treated as 2 separate problems. But when you think of them together, it allows you to do this kind of optimal design. And so again, engineering theory in this sense is suggesting this kind of optimal architectures for resilience. Another question you could ask would be something like Kahneman's question. So Daniel Kahneman, he was asking, suppose I want to do a joint system with AI and humans. Should I have the AI go first or should I have the human go first? I mean, his view was that you can combine humans and machines provided the machine has the last word. But some analysis we did showed that even if the AI agent has larger noise when making this global decision, if the human is following prospect theory, then in fact, this second architecture is better. So again, kind of using some ideas from decision theory, you can prove something like this.
What is prospect theory?
Prospect theory is something that Kahneman himself developed, actually. So it's a result in behavioral economics that shows, for example, that people weight losses more than gains, and other kind of probability reweightings. Okay, so those were kind of some stylized examples of kind of informing policymaking. Then I wanted to briefly talk about engineering theory as a policy lever itself. So Donald Mackenzie had this kind of famous book talking about financial markets, that the Black-Scholes kind of model of finance was not just an engine, was not just a camera, not just describing things, but actually an engine. And what he demonstrated was that, in fact, markets became more like the theory once the theory was published, which is kind of neat, right? It was performative. It was a self-fulfilling prophecy. So, like in Chicago, if you go to the Board of Trade, I mean, not anymore, but you know, the shouting, gesticulating, sweating, jostling bodies were actually enacting the theorems. And so this was, again, kind of a neat example where he showed the theory itself is a policy lever. So once you have the theory, it makes the thing more like itself. And one might ask, so can one do this purposefully? Like unclear if you can, but it's kind of a neat idea to think about. Another example is so Shannon's information theory. What he showed was that there's a separation between source coding, compression, and channel coding, which is error correction. And what's in between are these bits. Before the theory, there was no notion of bits. And so this kind of Shannon's universal interface allowed this notion of bits. And so if you look at this thing that I worked on for 6G wireless, it suggests, so from a policy perspective, we wanted things to be modular. But in fact, is that true in wireless systems? Unclear. I mean, they've started to do some modularity, but there's a desire for more modularity. And so again, to come to Ben's question, This is a question that's unknown. Is there any loss in technical performance by having modular design rather than monolithic systems in wireless communications? So if someone was able to figure this out, it would provide the technical support for the policy goal of modularity, which helps with diversified supply chains and so on. Right. So again, like a question that's unknown in engineering theory, but the answer would be useful. And then, yeah, I'm running on time, so let me skip to the end. I'll just briefly talk about computational positivism. So there's this idea that that you can kind of build technologies. That you can compute things, and if you can compute it, that's enough. You don't necessarily need a theory behind it. And the classic example of this is the so-called Needham's question. So a historian of science who was studying China and India and why they were ahead for 1,000 years, and then after the Industrial Revolution seemed to fall behind Europe. And Needham's kind of argument was that, one argument was that, for example, India was much more concerned about getting right answers rather than having theories. And there's strong philosophical reasons for this. In fact, things should be contextual rather than abstract and universal. But that's why you couldn't translate results from tracking where the stars and constellations are to like gravity and other things. And that didn't allow transfer of knowledge from one domain to the other, which is helpful for diffusion of technology. So that was kind of Needham's argument that theory helps with diffusion. And so, I was going to close with a little discussion of how theory can become practical. So our own work is in information lattice learning, this approach of composing music. So let me just, you know what I'll do? I'll just show you a little music.
We still have 20 minutes.
Oh, we do?
Yeah, it goes until 3:15. Oh,
okay. So maybe I'll talk a little more then. Mm-hmm. But let me, since I've skipped over to this, let me show you. Okay, so this is a song. They probably cannot see it. No, I can't.
Does it sound good?
It does. I can turn the sound up with my computer. So this is a song. Okay, so now I'm just going to take its melody. This is one of the melodies. It's probably isn't working well. Okay, let me just show you the creation. I think that'll be easier. So what I'm going to do is take, say, Happy Birthday's melody, take harmony.
Yeah, exactly.
Let me do like K545. This is Mozart's Piano Sonata. And we'll do like piano. Okay, so I just took these pieces. So the AI using information lattices did this decomposition, and I got these pieces, and I'm going to glue them back together. So I just did that twice. And so now hopefully we'll hear this. So this is Happy Birthday. Okay, we're not. So hopefully you could hear it on here. So you saw kind of the Happy Birthday melody and harmony, but the Mozart rhythm and so on. Okay, so
and you can actually then go back and say, this comes from this comes from this.
Yeah, exactly. Yeah, and so what I wanted to contrast, so that's how we do music composition as an example, and you can do it for other domains as well. But this is in contrast to large language model type music generation or other generative things, where it's unclear where the pieces are coming from. So it is very computationally positivist. You can generate stuff, but you have no idea what's happening, and there's no particular underlying theory behind it. Okay? And so Shannon himself believed that the promising new directions of information theory would come from research into AI. And so, like I was describing, so what we can do with information lattices is actually have a theory-driven approach to AI. So you can take things like, say, shapes and figure out that they have certain properties like red and blue or convex concave or number of sides. And this leads to kind of a full lattice structure of all the different knowledge you can essentially induce from partitioning. And this actually ends up being enough for doing this kind of music decomposition like I was describing, but also all kinds of other things. So you can drop pitches and keys and rhythms and so on. That's that decomposition. Then you can come back up and generate new things. So that's kind of the information lattice. And it's actually very powerful for a lot of other things. So you could do things like the simplest of image classification. So suppose I want to do the MNIST problem. I have digits, handwritten digits, and I want to classify what they are. So the best deep learning techniques require 28 examples of each digit. We can do it with 4 to get to 90% accuracy. So I literally have just 40 training points, and I can achieve human level performance as compared to the best of the deep learning, which requires at least 28 examples.
I mean, one of the things I hear a lot about large language models and network, network approaches is that it is sort of, they're definitely not how humans learn, right? Because you can tell a kid, this is a cup.
Right.
A 5-year-old will recognize this in every position without fail forevermore, right?
Right.
Whereas, you couldn't do that with a big network.
Right.
It sounds like you're getting a lot closer to how humans are actually knowing that that's a cup.
Yeah. So on the knowledge discovery side, the rules and laws that come out. So what we did was we took the 370 examples from Bach, and we tried to learn the laws of music theory. We could actually learn those in the same human interpretable form as a textbook. And we captured about 80% of the music theory curriculum that's taught in the first 3 courses at Illinois.
But what do you like in unstructured? You had no structure to start?
Yeah, that's right. So we just assume some kind of group theoretic thing that there are symmetries and stuff. And that's enough to learn these laws. So we're pretty task agnostic at the beginning. And we can use the same starting symmetries to learn laws in music as in chemistry, as in quantum chromodynamics, in a variety of fields. So we're starting with very basic, very, very basic stuff. And that's enough to learn these things because we're spending computational effort in structuring what can be learned, which is different than neural networks where they start with the possibility of learning anything, but then they spend a lot of computational effort in doing that learning. We're kind of flipping the script and saying, we're spending solving this computational group theory problem. We're structuring into the lattice that this is what is possible to learn. And then we don't need too much data or anything to do the learning.
But don't you have to have some structured concept of what music combinations can be? Or you're saying it's completely on?
Yeah, so again, it's just that symmetries like translation, rotation, and other rigid body transformations are probably relevant for music, just like they are for chemistry and so on.
But okay, so like when you say you get you're projecting that onto some kind of characteristics of the data, like you need to understand a chord progression or the concept of melody and harmony, but how would it know to articulate those particular concepts?
Oh yeah, sorry. So what comes out? Yeah, so what comes out of the algorithms are essentially these probabilistic rules that are cast in terms of set partitions. Then humans have to put words to them.
Right.
And so what we did was we had freshmen in a music theory class look at the histograms and convert them into words. And there were, I think, 25 students in the class. And so I think 3 of them got perfect scores on that assignment. 7 got 80% or more, et cetera. So that's suggestive that, I mean, they're not experts by any means. They're freshmen in a music theory class. And they were able to convert that representation into the standard words.
Like this representation, the algorithm's coming up with the representation on this component of something.
Yeah. And
then when you look at it, music theory, you say that's the chord progression.
Exactly. Okay. Yeah. So that's how we tested that it is human interpretable. And if you have, the professor do it, easy and, perfect score, et cetera. So.
Because it's not obvious that the brain would work that way either. like you could imagine that the chord progression
Mhm.
is a higher level concept where that your brain is imposing on a sort of deeper layer of sense.
Yeah. So actually, like the way our structure, it's the hierarchy itself is also interpretable. It is structured according to this lattice, and so like things like notes, scales lead to chords, lead to chord progressions. So the knowledge of chord progressions is expressed in the intermediate knowledge of chords, not in terms of the raw notes anymore. Yeah. Okay, so yeah, and coming back to like, is it human-like? It seems to be a little bit more human-like. So again, this is a harder image classification task. We're performing vision transformers and all kinds of stuff, almost human level. But also the inter-rater agreement is actually pretty close to. So we did this experiment with 5 humans. So it's right in the range of agreement among the humans also. So the algorithm is making roughly the same mistakes as the humans. So that's also kind of intriguing. And moreover, one can prove that the information lattice approach actually does optimal compression if you measure things symmetrically. So again, I'm not going to go into the details of the theorem or its proof, but you can actually do this kind of optimal compression in the semantic sense by doing this kind of dropping. Like this abstraction process itself is a compression that achieves the Shannon rate distortion thing. Okay, yeah, I did those sums. So again, so what I'm trying to argue is that this information lattice approach is kind of this white box AI that's directly human controllable and understandable. And it's moving away from this kind of purely data-driven, purely computational approach. It's being kind of acting as a counterweight to this computational positivism. So again, it's a role theory you can perhaps play as kind of a lever of strategy and policy rather than just a description. Okay? And our argument is that this kind of white box AI might facilitate diffusion of technology to different sectors. So when you're doing an LLM, I mean, it's good for language. If you try to do it for something else, it doesn't necessarily work. Here, we've tried it with music, same thing for chemistry, quantum chromodynamics, single cell RNA sequencing data. All seem to have that same basic symmetry structure. So it seems to transfer from domain to domain somewhat easily. So I think that's roughly what I had. Yeah, go ahead, Ben.
So I could go back to like you're saying it's moving away from purely computational data-driven approaches, but in some sense, like a transformer models, whatever, there's a structure, there is an algorithm, and then you train it. So it's not just purely like the structure.
Yeah, maybe that's too strong.
So when you're doing it, I mean, I don't understand what you're doing. I don't really understand what information lattice is, but you're basically saying you have a different way of some kind of algorithmic framework,
right,
that you then use data, and your thing is quite good and interpretable and much lower data use, energy use.
Yeah, correct.
Right.
Yeah.
So okay, but it's still in some sense they're just like a different component, but you're still training it, and it has to kind of.
Yeah. I mean, it is training, but I think there's a difference in kind between training on 1 billion things and training on 370 things. Right. So I mean, I think they are distinct, and one is very data heavy and data requiring, and very computational, I would argue.
Yeah.
The other is much less so.
But they're not. It's not symbolic AI, like where you're telling it what a chord progression is either. I mean, let the data speak, but you have a different algorithm that's much more efficient, basically.
Yeah. So yeah, I mean, I guess that's but what comes out also is symbolic in a sense. So it's not that everything is just in the neural weights that you don't know what to interpret from it. Here, I mean, the probabilistic rules are literally the laws of music theory. And so those then we're using for composition for whatever downstream. So I still think there is a difference in kind, but I mean, your point is taken. Yep.
I have a couple of questions.
Yep.
First of all, very provocative. Thank you so much. One question I have is you've talked about sort of the virtues of these limits. I wonder if you could talk about the downsides of these limits. No one thought you'd ever be able to run a mile in less than 4 minutes.
Yep.
No one ever thought we'd be able to fly until 1903, things like this. So do they impose constraints on us that actually hurt us long term?
Yeah.
So that's one question I have. The other question I have is thinking about these limits a bit more from just a social point of view it.
Right.
Because you are talking about socio-technical systems.
Yep.
I've always thought of law as a limit on human behavior.
Mhm.
But it's not a law the way you've been talking about it in terms of a limit, and maybe it's not absolute. But it also seems like, is it a valuable guide to have a law like that if it's so easily so easily broken if you want to do that, or something that's a law but maybe a limit but maybe a little bit more open to interpretation. So how do you think about that? The two things. One is like, what are the downsides of these things for like, limiting human imagination?
Right.
And also, is law a form of a limit, and what are its weaknesses?
Yeah. Let me start with the second. So like I was describing, like one function socially of these fundamental limits is to goad people to work harder. So, people spent 50 years trying to approach the Shannon limit in communication. They kept at it. Like, I don't think people would have worked so hard or worked so long had they not known what that limit was. So these fundamental limits have that kind of motivating property, it seems. On the other hand, I think you're right that, sometimes they can also limit you, but I think that's sometimes people who are kind of they're doing like I don't want to use kind of Kuhnian terminology, but that's what's coming to mind. Like people who are doing normal science, I think they think the limits are the limits. But I think people who can do the transformational thing, the revolutionary thing, they can transcend those limits also. So like I was describing, like moving closer improves the channel. Like if you're just working in the diagram, you wouldn't think to do that. You would just try to find the codes that are the best, like for the channel you're given. And so, like it seems to me that, the kind of the playing field that the fundamental limits establish kind of force you almost into like always doing normal science. Whereas, I think you can move beyond that, and hopefully people are willing to do that. So you change what is fundamental, and then you have a bigger playing field essentially.
Mm-hmm.
With respect to kind of legal systems, again, I think people do try to push against them as close as they can, or they try to change them eventually, right? And it feels to me like it's a similar social process. Just kind of anecdotally, you try to go just 7 miles an hour faster than the speed limit because you don't think the cop is going to pull you over. Then when you go 11 miles per hour faster than the speed limit, you might get pulled over.
Mm-hmm.
Right? I feel like people do treat it somewhat the same. That you try to kind of follow the rules somewhat and try to think about ways to circumvent them as well, and then maybe change them and increase the speed limit from 70 to 75. So I feel like there are certain similarities. I don't have very clear thoughts on precisely so.
Yeah. Okay, thanks.
The challenges for a lot of systems, they don't have the Newton's third law. When you can distill, I think a lot of this kind of distinction between physics and engineering in a sense.
Yeah.
When you can actually have the limits, like Shannon, then say within the system, that's a real fundamental limit, right? But when you say, limits, fundamental limits can be surpassed, then that just really means it wasn't a fundamental limits in a sense, right?
No, that's what I mean. So there's two parts to the word, right? Fundamental and limits. So the fundamental would have to change for the limit to be surpassed, right? So when the fundamentals are fixed, then the limits hold, right? But you have to kind of change the axioms. You have to change the closed deductive system. You have to change the thing. Then you can do better.
Right. But then the reality is there are only very few cases where we know fundamental limits, and that has helped. But for many cases, we don't know. Yeah. And even like I think a lot of examples of this single famous example. Okay, 4-minute mile. For a long time, people thought that was a limit.
Right.
What is the limit for a 100-meter dash? We don't know.
Yeah.
What is the limit for population, total population on this planet? We
Right.
don't know. And there was this very famous population bomb
Yeah.
book
Yeah, yeah.
that facilitated one-child policy.
Right.
And then you have Moore's law, which is something that we think quite a bit these days, think about technology progress. And that's also, I mean, I had some limit, but when the Moore's law was proposed, quantum mechanics was known, but you're very far away from the limit.
Yeah.
But it was that's, in some sense, it's actually impossible to see exponential growth can hold for that long and up to today.
Yeah.
And so I think, one question I've been always wondering is that how do you know there is a limit, and how do you assess it's actually far away or very close by?
Right. Yeah. So some of the examples we were using are more phenomenological laws rather than engineering systems theories. So, this kind of how fast can you run question is not an engineering systems theory. An engineering systems theory would be how quickly can any system run, or move from one point to another, right? And so those are two different things, it seems to me. And I mean, I agree with you that there are not limit theorems for so many things. I tried to go through some examples.
But even like how any system can run, I mean, that wouldn't you say the limit is speed of light?
No. So there's so if you define your deductive system to have like friction and air, whatever, and like all those things, then I mean it's much slower than light, right? When matter moves, it has to move slower than that.
Correct. So that's where
So you have to define that kind of system for which you are finding the limits.
Correct. Yeah.
And so I mean that's the fundamental part, right? So what is the playing field? Is it that you have to run on a surface which has friction, you're moving through air? There's some like metabolic efficiency, like Carnot's limit, etc. Right? I mean, once you establish those, then you get an engineering systems theory. Not without that. Yeah.
So if that's the case, what kind of system should we look for where we could find out what the limits are?
Yeah, so it seems to me that a lot of informational kinds of systems, whether it's creativity, decision-making, communication, etc. I mean, those seem to have those kinds of things. And like, broadly speaking, a lot of these limit theorems use somewhat similar proof techniques. They are very much about some sort of phase transition kind of argument. And so, like a lot of things, like including many complex systems, have this kind of phase transition-like property. And so those are the ones that we know how to do limit theorems for. I mean, I'm sure there must be some other ways of doing this kind of thing, but those are the kind of generally known ones. So, but yeah, I mean, broadly, like AI, like a lot of the functions of AI, we do seem to have at least a path to such limit theorems. So all the capabilities we associate with cognitive processes, memory, creativity, decision making, et cetera, et cetera.
Yeah, well, we could discussing for just keep going. This is very good characteristics of Ryan Institute seminar, which is thought-provoking. Okay, I don't know if you guys feel. Yeah. I gotta say, just last comment, that music demo is very important because I think one of the best things that Ryan Institutes are known for is the co-directors are extremely talented in music, except one, and the world famous band Bracket. For those of you who don't know, follow them on TikTok. Did you get that? You gotta get out of it. All right. Anyway, thank you so much, Lav.